In this video, we're going to look at how to calculate the effective nuclear charge for a given electron in an atom. So we've seen previously that we can calculate the effective nuclear charge by calculating the actual nuclear charge and subtracting any electron shielding. So to help better explain what effective nuclear charge is and the periodic trends, we're going to actually look at how to calculate the numeric value for Zeff. So to calculate the effective nuclear charge, let's first look at the actual nuclear charge. That's pretty simple. For each proton in the nucleus, we get +1 for the actual nuclear charge. So if an atom has three protons in the nucleus, its actual nuclear charge would be 3. So the Z actual is equal to the atomic number for that atom. Calculating the electron shielding, of course, is a little more difficult. We have to look at where an electron is in the atom in order to determine its shielding value. The closer an electron is to the nucleus, the more shielding it will provide, the larger its shielding value. So, in other words, the greater the probability of finding an electron close to the nucleus, the more its shielding value. Put another way, the smaller the electrons in number, the more shielding it will provide. So, of course, that means that core electrons provide more shielding and block the nuclear charge more effectively, whereas valence electrons provide less shielding. So these will have a smaller shielding value because they less effectively block the attractive force between a given electron and the nucleus. So in order to calculate the numeric value for the effective nuclear charge, we use what are called Slater's rules. Now these don't give us an exact value, but they can give us a pretty good estimate of what the effective nuclear charge is. Now again, this is the effective nuclear charge for a given electron in an atom. So we need to specify exactly which electron we're calculating the effective nuclear charge for. So we assign numeric shielding values to each electron in an atom based on that atom's position relative to the nucleus. The closer the nucleus is to the nucleus, the larger the shielding value. So here are Slater's rules. Now they look pretty complicated, but they're not too bad. If you would, pause the video for a minute and read through them. Okay, let me point out just a couple of things. First of all, we want to assign a numeric value to each electron. Each electron in the valence shell will get a value of 0.35 nuclear charge units there for that electron. If an electron is a core electron, but it has a quantum number 1, it's in one shell below the valence shell, it gets a 0.85 value for those electrons. If electrons are 2 or more shells lower, so where they're core electrons, but they're 2 or more shells below the valence shell, each electron there will get a value of 1 electron unit. Now I'm not going to get into D and F electrons here, but essentially we assign these values to the electrons and then we subtract the shielding value from the overall nuclear charge. Now again, before you turn off the video, let me practice a couple. Let's practice a couple and you'll see it's not so bad. Let's determine the effective nuclear charge and therefore the electron shielding value by the outermost, so the highest energy electron in each atom in the second period, as well as sodium. So let's determine the effective nuclear charge for each of these atoms, as well as sodium. So we want to use Slater's rules to figure out what is the shielding value. Now, if you would, why don't you pause the video and just give it a try. See if you can calculate these, what you would get for each atom here before I work through it. So pause the video, try a few before you look at my worked examples. So let's take a look at the effective nuclear charge for lithium. Here's the electron configuration, and we want to determine the shielding felt by this outermost electron. So I've got the core electrons in red, the electron of interest is blue. So let's assign some numeric values. Well, these are core electrons, and this is the n equals 2, This is n equals 1. So each of these will get a value of 0.85 because they're one n number less than our valence shell. So we have 2 core electrons. Each of those are 0.85, so we have 0.85 times 2. Now this electron can't shield itself, so we don't calculate any shielding value for the electron of interest. So what we do is take the effective nuclear charge is equal to the actual nuclear charge. Lithium has 3 protons, minus 0.85 times 2 is 1.70. So the effective nuclear charge is 1.30 for lithium. Okay, let's practice a couple more. For beryllium, again, same number of core electrons, but we've added another valence electron. So the 2 core electrons, again, they're one n number smaller, so they get a value of only 0.85 times 2. And this electron can shield our electron of interest, but this electron, the black one here, is in the same valence shell. Remember, electrons in the same valence shell get a value of only 0.35. So that means that this electron here shields less effectively, so it has a smaller shielding value than these 2 core electrons. That's why it's a smaller number. So if we add these together, we get the shielding value. So we take the actual nuclear charge 4 minus the 1.7 from the core and the 0.35 from that valence electron, and we get 1.95. Okay, let's keep going. Now boron, here's the electron configuration. The 2 core electrons, again, 0.85 times 2. Now these 2 valence electrons, they're in the valence shell, so we get 0.35 times 2. So the effective nuclear charge is actual 5 minus 1.7 from the core plus 0.70, and so we get 2.60. Okay, so again, these electrons do shield, but less effectively than the core. So the actual nuclear charge is increasing at a greater magnitude than the shielding value. So overall, the effective nuclear charge, as you can see, keeps going up. Okay, carbon, we get 0.85 for each core. Our valence electrons, we have 3 of those, and so we get 6 minus the shielding values, we get 3.25. Okay, nitrogen, again, we're adding another valence electrons, but our core electrons are the same. So we have 0.35 times 4, 1, 2, 3, 4. And again, we're calculating the attractive force, the effective nuclear charge of this outermost electron. We could do it for any of these, but here we're just interested in that. So our effective nuclear charge is 7, because there are 7 protons, minus those shielding values, and we get 3.90. Okay. Oxygen, same thing. We get 5 valence, so oxygen's effective nuclear charge, 4.55. And fluorine, our core, here we have 6 valence electrons. Each one gets 0.35 because they don't shield as effectively as the core. And we get 9 minus 1.7 plus 2.10, 5.20. And neon, again, same thing, same number of core, 7 valence. So we get 10 minus the shielding values, we get 5.85. Now, let's do one more, and this one's interesting, sodium. Now with sodium, we started a new shell, right? So now all of these guys are core. So these guys, now this is the n equals 3, these are n equals 2, and this is n equals 1. So now these electrons right here, what value will they get? Well, they're more than one n number less, so they get a value of 1. Now it's not 0.85, because again, it's more than one n number less. So we get 1.0 times 2. All 1, 2, 3, 4, 5, 6, 7, all 8 of these are going to have a value of 0.85 because they're one n number less. So they do shield, but not quite as effectively as these guys. Again, these are closer to the nucleus, so they have more shielding value. So we have 0.85 times 8. And again, this electron can't shield itself. So we add those together, and all of these are core electrons. So notice that the effective nuclear charge here only increased by 1, but we had a large increase in the shielding value. So the effective nuclear charge for sodium drops significantly. So let's put this into a table and look at the effective nuclear charge that we calculated. From lithium to neon, again, from lithium to neon, this is across a period. The effective nuclear charge increases as we go across the period. That's because the actual nuclear charge increases, but the shielding value, due to the valence electrons, is not increasing at the same magnitude. So these electrons get pulled tighter to the nucleus. But once we start a new period, now we have a whole new bunch of core electrons, so our shielding value jumps way up, uh, but our actual nuclear charge does not go up as significantly. So it drops significantly.
So be sure that you can describe why the effective nuclear charge increases across a period and why it decreases once we start a new period. And be sure you understand this trend very, very well because we use effective nuclear charge to explain a lot of the properties of various atoms.